Is Magic Mike here with the Crypto Playground, and today I want to talk to you guys about Bitcoin. So a lot of folks have not spent the time to understand the genesis of cryptocurrency, which is Bitcoin, and a lot of folks don't understand the difference between blockchain and Bitcoin as being two unique ideas that have kind of almost gone in their own way, although they are currently and always will be complementary to each other. Blockchain is its own entity that is not uniquely just tied to Bitcoin. So we're going to have the conversation kind of starting off with the history of blockchain, because like Bitcoin, blockchain is a technology. All right. So when you're talking about Bitcoin, we're not just talking about a currency. We're talking about the adoption of a technology that can be used to store assets, and also to act as, in some capacities, the blockchain enables the transfer of digital currencies. All right, so we're going to start off with the history of blockchain, just to illustrate that blockchain concept did not just start with Bitcoin. So here we see that the blockchain idea actually started in 1991. It says a cryptographically secure chain of blocks is described for the first time by Stuart Haber and W. Scott Stornetta. In 98, a computer scientist, Nick Sasbo, works on BitGold, a decentralized digital currency. In the year 2000, Stefan Kunst publishes his theory of cryptographic secure chains, plus ideas for implementation. And then Satoshi Nakamoto, which is a pseudonym, comes along and creates a white paper in 2008 that establishes the model for a blockchain. And in 2009, Nakamoto implements the first blockchain as the public ledger for transactions made using Bitcoin. Going further, in 2014, blockchain technology is separated from the currency, and its potential for other financial inter-organizational transactions is explored. Blockchain 2.0 is born, referring to applications beyond currency. The Ethereum blockchain introduces computer programs into the blocks representing financial instruments such as bonds. These become known as smart contracts. So, as you can see, it did not start with Bitcoin. One aspect, especially if you're getting into this crypto space, which everybody, I think, in the future will be kind of slowly ushered into this digital space, as you know, we see Samsung adding digital wallets to their devices with the Engine coin. There's talks about Apple actually integrating a Bitcoin wallet into their phone's wallet. PayPal and Square, Visa. There's a lot of adoption of this technology, and a very small percentage of the world actually is aware of what this really is. It's a really foreign space. But in order to understand the genesis of anything, we got to go back to the beginning. And the beginning is really this Bitcoin white paper, right? And I always encourage folks to go and read the white paper, because it kind of gives you a little bit of an insight into what the problem Bitcoin was trying to solve, and then also understanding that around the time when Bitcoin came out, we had that financial crisis, and there was all came from these banks kind of having too much control and running rampant with it. So this kind of was very timely when it came out, with the distrust in the financial system and the concern about a central group of folks controlling our wealth. So we're going to go over this white paper and talk about some of the components of it. I've kind of highlighted a few things here that I just want to touch on, but I highly encourage you guys to go and Google this Bitcoin white paper and read through it. It's 9 pages long. It's not that difficult to get through. I'm going to try to break down some of the more difficult concepts in here, because I know if you're not technical, you're probably not going to know what some of the things in here actually mean. All right, so I'm going to try to break those things down for you a little bit as we go through this. All right, so let's get started. So here it is, the Bitcoin peer-to-peer electronic cash. This paper was written by Satoshi Nakamoto, which was a pseudonym for the individual or individuals that created Bitcoin. So let's go through the entire abstract. There's going to be some points in here that I'm going to break down for you because it's going to be relevant throughout the rest of the document. So a purely peer-to-peer version of electronic cash would allow online payments to be sent directly from one party to another without going through a financial institution. Digital signatures provide part of the solution, but the main benefits are lost if a trusted party is still required to prevent double spending. So let's stop there. Let's talk about that for a second. So first piece here, we're trying to send direct payments from me to somebody else without going through a bank. Normally, I would have to go through some type of intermediary if I want to send an ACH transfer. Lots of people in that process, and time and fees. We're trying to enable a system where we can transact directly from me to you. Digital signatures are part of the solution. So the question is, what is a digital signature? So a digital signature is a representation of your real world signature, but it's done using what's called digital certificates. So when you create a digital signature, you are doing that with something that you specifically and solely control, and you're using that digital certificate to sign a transaction using some type of password or PIN code. And the uniqueness behind it is that only you have access, just like your bank PIN code, only you have access to that information to enact that digital signature. So if you've ever done a financial, a document online, maybe bought a house or something like that, they'll send you documents and then they'll say, hey, click this. By clicking this, you are kind of digitally signing it, because you had to log into a platform before you got to the point where you can actually digitally represent yourself on that document. So there's a technical way to do that using what's called digital certificates. Essentially, you have what's called a private key, and that private key has a public key counterpart that's accessible by everybody else. And what you essentially do is you take your private key that only you control, and you take that, you digitally sign by typing in a PIN code or a password, and then other people can take the other piece of it like a puzzle. Like if I have these two pieces and they go together, if this is my private key and this is my public key, anybody can verify that I actually signed it by using the corresponding public key that everybody has access to, like a phone book. They can say, let me take his public key and verify that he actually signed this, and that's how we verify that a transaction actually originated from you, because you had to know something other people wouldn't know to utilize your private key to sign something, which can be verified. All right, so digital signatures provide part of the solution, but the main benefits are lost if a trusted party is still required to prevent double spending. Double spending problem, I don't think they go into that too much into this paper what it is, but essentially what double spending is making sure that if I write a check to John to withdraw a balance from my account, I can't write a check to Steve for that same amount and spend that money twice. So normally banks provide that service for us. They mediate those transactions. So if you swipe your debit card here, they immediately, reserve those funds for the person you swiped the card from. And if you were to swipe your card again, you would have to have either additional funds, or the transaction would get denied, or you're going to overdraft protection. In this case, in the crypto space, there is no bank, and no one has been able to solve the double spend problem with digital transactions before. But that's one thing that Bitcoin was able to achieve. So it says, we propose a solution to the double spending problem using a peer-to-peer network. The network timestamps transactions by hashing them into an ongoing chain of hash-based proof of work forming a record that cannot be changed without redoing the proof of work. So let's talk about hashes real quick. So hashes is pretty much an algorithm that is able to take any length of information and run it through kind of a grinding mill and spits out a fixed length bit of information on the other side. So let's just imagine if I take a big old piece of beef and I grind it up and I put it inside of a hot dog, casing. That's hashing, right? So we're taking a lot of information. In this case, we're taking a lot of financial transactions, inputs and outputs. And then, this is from a lot of folks that are transacting, 35,000 transactions a day. And then every time that we fill up a block, then we run that through this grinder and then we spit out a fixed length hash, which is let's call it a hot dog for the sake of this conversation. When a hot dog comes out, we timestamp it to say that this hot dog represents all the transactions that has occurred in this block. And now if we make any changes, if we go back to that, big, piece of beef and try to make any modifications, it will change the result of the way that hot dog looks and smells. And then you say, hey, something happened here. That's what we do with hashing, and that's where we get the integrity from, because things cannot be changed once that hash is produced, and that's where we can verify whether the integrity of the network is maintained. So the network timestamps transactions by hashing them into an ongoing chain of hash-based proof of work, forming a record that cannot be changed without redoing the proof of work. The longest chain not only serves as a proof of the sequence of events witnessed, but proof that it came from the largest pool of CPU power. As long as a majority of the CPU power is controlled by nodes that are not cooperating to attack the network, they'll generate the longest chain and outpace attackers. The network itself requires minimal structure. Messages are broadcast on a best effort basis, and nodes can leave and rejoin the network at will, accepting the longest proof of work chain as proof of what happened while they were gone. So we're going to get into that more later in this paper. So here's the introduction, and we're going to touch on a few things here. So commerce on the internet has come to rely almost exclusively on financial institutions serving as a trusted third party to process payments. So this suffers from the inherent weakness of the trust-based model. So we're looking at right now, the only way you can transact is by relying on a third party to facilitate that transaction, which means you have to solely trust this third party against corruption, political motivation. You have to trust a lot of different aspects, specifically the financial institutions that are doing these transactions or facilitating transactions. There's a lot of trust that you have to blindly relinquish, as you work and making financial transactions. So because they're doing all this mediating for you, the cost of mediation increases transactions costs, limiting the minimal practical transaction size and cutting off the possibility for small casual transactions. So just imagine that you wanted to buy something for $1 from somebody on the other side. You want to send $1, to a family member. There's a lot of additional fees that's tagged on to send that dollar, because somebody in the banking system has to make sure you have the dollar. They have to verify where the dollar is going. There's a lot of people in between there that needs to pull out fees because they're providing some type of network services, and all of a sudden that dollar becomes $5 by the time you get it from point A to point B. So we cannot do microtransactions on the current financial network because of the fees associated with providing that centralized service. These costs and payment uncertainties can be avoided in person by using physical currency, but no mechanism exists to make payments over a communication channel without a trusted party. What is needed is an electronic payment system based on cryptographic proof instead of trust, allowing any two willing parties to transact directly with each other without the need for a trusted third party. So they propose a solution to the double spending problem using a peer-to-peer distributed timestamp server to generate computational proof of the chronological order of transactions. The system is secure as long as honest nodes collectively control more CPU power than any cooperating group of attackers. All right, so let's talk about that real quick. So blockchain is literally a ledger of inputs and outputs, deposits and withdrawals. So just imagine that this is, block, right? And all I'm doing is I'm taking this block and I'm writing, he deposited this much, he withdrew this much, he transacted this much, and I'm just writing down all these transactions on this thing as it goes on across this peer-to-peer decentralized network. There's all these computers that's collectively recording all this information. So once this block is full, now I need to attach this to the network of existing blocks. But before I attach it, because everything here in this blocks have already been verified and trusted and vetted by a bunch of computers, so now I have to take this, I have to verify all the transactions. A bunch of computers have to get together collectively and say that they agree on the validity of all the transactions and digital signatures. And then once we are able to do that, then we run this through a hashing algorithm. And then once we hash it and the hash is verified by, there's a requirement to have a certain number of leading zeros, that kind of creates the difficulty of doing that mining or proof of work process. Once that's achieved, then we can take it and we can append it to the long list of previous hashes that have occurred. And that kind of creates those blocks. So just as long as there's more honest nodes that are using their CPU power to solve these math problems, to add to the connection of all of these previous blocks, then a group of attackers will have to have like a substantial amount of effort to outpace the honest nodes, which when we think about honest nodes, we're thinking about a global distribution of computers everywhere and large corporations that are using GPUs and ASICs chips and all kind of stuff like that, with massive amounts of energy and computational power to solve these math problems. A group of attackers would have to do a whole lot to beat that. All right, so transactions. So we define an electronic coin as a chain of digital signatures. Each owner transfers the coin to the next by digitally signing a hash of the previous transaction and the public key of the next owner, and adding these to the end of the coin. A payee can verify the signatures to verify the chain of ownership. All right, so they have a little example here. I know that might be a little bit confusing for some, but just think about it as a bank account number. All right, so and that's, we'll think about that as the public key. Normally, if you want to make a transaction, you got to give somebody your bank account and your routing number, right? So we'll just kind of use that as a frame of reference. All right, so we'll say that we want to send this to somebody. So this is a transaction block here. We want to send this to somebody, so we use their public key or their bank account number, and then we combine that with the hash, which is pretty much all of the transactions that have occurred previously are all represented by a fixed length, alphanumeric representation called a hash. So we combine the person you want to send it to with this hash of all the previous things, and then we digitally sign it. So what we do is we take our private key and then we sign this information saying, yep, this is who I want to send it to. Yes, this is the record of all the previous transactions that have occurred. And then we send that on to the next person. So now they own this Bitcoin because I said I want to send $10 to this guy to his routing number, and I'm gonna take the previous snapshot of my bank account and I'm gonna hash it saying, look, I do have $10 to send because here's a snapshot of my financial record. I want to deduct that from here, and I'm going to sign this using my private key, which only I control, and I'm going to send that over to this guy. So now he can take my public key and he can verify whether or not this information is true, because I've signed it with my private key. He has a corresponding public key, and then he can verify that. So here you see the transaction goes on. So now this whole block here is now hashed, right? So this is just kind of a small piece of a larger, block of a bunch of different transactions. But this whole transaction block here can be hashed, and then the same thing goes on here. So we hash that here. He now wants to send it to owner 2's owner 2, so he gets his account information. He combines that with the history of the previous transactions, which here we sent some money. and then he signs it with his key, and then he sends it on, and the same thing happens again. And that's how the blocks are created. So here we talk about the only way, and we talk about the double spend problem here, because usually a bank will have to get involved to verify that we haven't spent the same amount of money twice. So the only way to confirm the absence of a transaction is to be aware of all the transactions that have happened. So in the mint-based model, the mint was aware of all transactions and decided which arrived first. To accomplish this without a trusted party, transactions must be publicly announced, and we need a system for participants to agree on a single history of the order in which they were received. The payee needs proof that at the time of each transaction, the majority of nodes agreed it was first received. So here we're saying that we need the history of the blockchain needs to be maintained, in a synchronous way, a chronological way that every node that participates in this peer-to-peer network can agree upon. That's why these hashes are so important, because this is literally a snapshot of the entire history of the blockchain. So you have full nodes that capture all the transactions that have happened. Then you have these light nodes that just capture what's called header information, which is just kind of top level data about transactions that have occurred. So this is the agreed upon continuous snapshot where we can always go back and say, John had $100, then he had $50 in the snapshot, then he had $25, then he got another $100, and then we can always see the history, and that's how we know whether or not a person has the ability to make a transaction or if they're broke. We can kind of see that. And that's always agreed upon, because a whole bunch of computers have to get what's called consensus to say that the record of everybody's transactions and account balances are correct. And once that consensus is achieved, that's the only time that information is attached to the blockchain. So the solution we propose begins with a timestamp server. A timestamp server works by taking a hash of a block of items to be timestamped and widely publishing the hash. Timestamp proves the data must have existed at the time, obviously in order to get into the hash. Each timestamp includes the previous timestamp in its hash, forming a chain, with each additional timestamp reinforcing the ones before it. So what we're saying here is exactly what we've been talking about, is that this network, once information is put inside of a hash, that hash cannot be modified. So if you have, once you say, I agree that all the transactions in here are correct, I don't want to put this entire thing, inside, my record. So I'm going to do is I'm going to create a mathematical representation of this called a hash that is smaller and fixed in size. And I'm going to say that small hash represents everything in here. If I change one thing in here, the hash no longer represents this, and this is what breaks it. But now if we have, 10, blocks that get added to this, now the integrity of this particular hash is 10 blocks back is even greater, because there's more work that has been done previous to that. So if somebody wants to compromise your bank account balance as of a week ago, well, guess what? There's a whole lot of blocks that have occurred on top of that since that week ago. So they would have to go back and do all the math for every single block that's been created to just compromise this one, and that takes a whole lot of time and a whole lot of computational power, which kind of prevents folks from doing that. So we have what's called a consensus mechanism, and it's how all the nodes or computers that work in this network come to agreement that something should be added. In this case, we do what's called a proof of work. So the proof of work involves scanning for a value that, when hashed, such as with SHA-256, which is just a hashing algorithm, the hash begins with a number of 0 bits. So the average work required is exponential in the number of 0 bits required, and can be verified by executing a single hash. So they have to, normally the way they create the difficulty in the hashing process is by determining the number of zeros that has to be before the final value. And the faster the network is able to solve these problems, say the computational power of the systems gets stronger and stronger, then the more difficult the problem becomes. And that's why the miners, the computers or the owners or the businesses that do the mining activity are incentivized by solving this problem and being rewarded in Bitcoin for solving the problem. So Bitcoin has a fixed supply of 21 million coins that will ever be created, and that's how the coins are generated, is by these computers using their CPU power to solve these mathematical problems. And then once they solve that problem, they're rewarded with Bitcoin, which is pretty much the minting process that we have in our Federal Reserve. That's the printing of the new Bitcoin, but with a fixed ceiling. All right, we implement the proof of work by incrementing a nonce in the block until a value is found that gives the block hash the required 0 bits. So a nonce is just a random extra pieces of information that's added into the block until we get the required number of leading zeros. So for example, let's say if I gave you a math problem and I said the math problem needs to equal 128, right? And then I gave you 64, 12, and 15, and then some other random number. And you have to just keep guessing what that additional random number is until you get to the required number. And once you get to that required number, you won, you know. And that's what the computers are doing. There's a required number of leading zeros, and then they have to take this nonce, which is just kind of randomness, and continue adding that into the mix of the representation of all these transactions until they get to the point where they say we've achieved the number of required leading zeros. All right. So the proof of work also solves the problem of determining representation and majority decision making. If the majority were based on one IP address, one vote, it could be subverted by anyone able to allocate many IPs. So there's decisions that need to be made in the blockchain network, like upgrades, the accuracy of information, things of that nature. And they had to come up with a voting system. Like, how do you determine that with 1,000, 2,000 nodes, that are all participating in this consensus network? How do you come up with a process for everybody to vote and say this information is accurate, we should do this upgrade? How do you do that? And they said, okay, well, if we did it by IP address, then somebody can, take majority of the vote by, creating a lot more IP addresses, which is very easy to do. So the approach that they took on proof of work is essentially one CPU, one vote. So you have a CPU that's participating, providing hash power to the network, gets a vote in the integrity, gets a vote in the upgrades, gets a vote in all the different aspects of maintaining the network. The majority decision is represented by the longest chain, which has the greatest proof of work effort invested in it. If a majority of CPU power is controlled by honest nodes, the honest chain will grow the fastest and outpace any competing chains. To modify a passed block, an attacker would have to redo the proof of work of the block and all blocks after it, and then catch up with and surpass the work of honest nodes. It would show later the probability of a slow attacker catching up diminishing exponentially as subsequent blocks are added. To compensate for increasing hardware speeds and varying interest in running nodes over time, the proof of work difficulty is determined by a moving average targeting an average number of blocks per hour. If they are generated too fast, the difficulty increases. So again, if it happens too fast, the blocks are being mined too fast because the computational power is increasing every year. Phones are getting faster, computers are getting faster, so they just increase the difficulty of the math problem. So quick look at the network. So to set up the networks, you have to do these following things. The steps to run a network are as follows. New transactions are broadcasted to all nodes. Each node collects new transactions into a block. Each node works on finding a difficult proof of work for its block. When a node finds a proof of work, it broadcasts the block to all nodes. Nodes accept the block only if all transactions in it are valid and not already spent. Nodes express their acceptance of the block by working on creating the next block in the chain, using the hash of the accepted block as the previous hash. All right. So The reason why I talk about the longest chain is because there's something called a memory pool, and sometimes there may be two competing blocks that are created at the same time, where one person has received some transactions that have not made it across the entire network, and in order to make sure that the network maintains integrity, even if there is a difference in the information that these nodes have received, they store this information inside of a memory pool when there's a difference between two blocks, or maybe transactions that were received here but not here. And when it sees that one block is continuing to grow and the other one is there's no consensus on it, then it takes the one that has the longest chain as being the agreed upon blockchain, and that's the one that will continue on working. We talked a little about the incentives that when somebody is doing the mining process, they look at it as being analogous to a gold miner expending resources to add gold to circulation. In this case, we're using CPU and electricity to continue to add Bitcoin to the circulation. It says once a predetermined number of coins have entered circulation, which is 21 million, the incentive can transition entirely to transaction fees and be completely inflation free. So people ask the question often, like, what happens when all the Bitcoin is minted? What's the incentive? Well, now we go to transaction fees, which the transaction fees are always negligible in comparison to the traditional financial market, and the transactions will occur a lot faster than the actual traditional financial market. So the rest of this paper talks about some of the technical stuff, reclaiming disk space. Bitcoin uses something called a Merkle Tree, which is pretty much a database for storing information, and every so often it trims this tree to keep the space down. It's pretty interesting here. We talk about a block header. A block header with no transactions would be about 80 bytes. If you suppose blocks are generated every 10 minutes, that would be about 4.2 megabytes a year. And they just kind of talk about how even though there's a lot of global transactions going on, we're still keeping a fairly small size to the blockchain. A lot of people, imagine that this thing is terabytes or super unsustainable as far as storage, but it's actually really small with the database model that they chose. They talk about things like simple payment verification, how you verify payments, combining and splitting values, how the microtransactions can occur on this network. They talk about things like that, and then privacy, which is pretty much an interesting section here. It talks about the traditional banking system model achieves level of privacy by limiting access to information to parties involved and the trusted third party. The necessity to announce all transactions publicly precludes this method, but privacy can still be maintained by breaking the flow of information in another place by keeping public keys anonymous. So what they show here is the traditional privacy model, and pretty much this line right here acts as like the firewall. So you have to have your identity tied to your transaction, meaning your bank account has to have your name and all your information, and that's going to be tied to every payment that you make, and that information goes to a trusted third party and then to a counterpart. The trusted third party might be your bank, and then that goes from your bank to whoever, and all that information is kind of buried off from the public, so people can't see. John Doe that's not involved in your transaction can't go and look at all this information without your permission. The new privacy model separates your identity and puts the firewall between the transactions and the public. So you can go and, like, for example, I can show you if I want to, like, Block Explorer. So this is kind of like the public, blockchain, and I can see here there's some transactions that went on, but I can't see, I can see the transaction, but I don't know who it belongs to. But I see some folks were sending stuff, and I can't really tell. They sent 2000 HNS. There was no fees. They sent it on this date. There's absolutely no public information or anything that's tied or private information tied to that. So I can't really tell who that belongs to. So that's pretty much the variation inside the the models. Interesting thing to look at here is, let me see here, where is that? Okay, so as additional firewall, a new key pair should be used for each transaction to keep them from being linked to a common owner. Some linking is still unavoidable with multi-input transactions, which necessarily reveals that their input were owned by the same owner. The risk that if an owner of a key is revealed, linking can reveal other transactions that belong to that same owner. So what they're talking about there is, for example, if you were to utilize Coinbase and you had to do a KYC and know your customer process to sign up to Coinbase, and then you bought some Bitcoin on Coinbase and you transferred the Bitcoin over to another wallet, and that wallet has a certain address tied to it. The way that this is set up, where the transactions are public but the identities are hidden, what they're saying here is that if you had multiple transactions and you didn't use a different key pair, which is pretty much what we looked at here. Actually, this doesn't show. Hold on, there you go. So you might have an address. Obviously, it says Coinbase here. So you have an address. When you use a different key pair, that means you're using a different public address each time, which makes it difficult, because if I pay John and my address is 1, and I pay Steve and my address is 2, and I pay John, like Ken, and my address is 3, then it makes it difficult to say, well, 1, 2, and 3 are all, different addresses that, the payments are originating from. So who owns this? That makes it difficult. And that's why they said you should use a different key pair for each transaction. And that's sometimes facilitated through your wallet. Your wallet, we'll talk about that later, or through your exchange, you can use different key pairs. When you use the same key pair over and over, if I make a payment, if I say that I make one payment using 1, and I make another payment to somebody else using 1, I make another payment else to somebody else using 1, then eventually you can kind of figure out that I made all those payments, and that's what they're talking about there. So again, this is the Bitcoin white paper. I highly encourage folks to kind of go back and take a look at it. This is like the start of the whole crypto phase, and this is the kind of the genesis of kind of where we're at now. So take time to go back and read it, and we'll get another video later on and kind of talk about some of the other aspects of investing in crypto. And I hope you guys learned something from this. If you did, please like and subscribe to the channel. If you have any questions or want me to go into a particular thing, then please leave something in the comments, so that way I can create more content for you. All right, thanks.